are in the process of looking at specific, discrete probability distributions. Our purpose for doing this in our course is that we need those probability reasonings when we start analyzing and looking at discrete data, counting survivals, counting successes, counting whatever we count. And I assure you, you're going to count a few things in your future or have some counts presented to you by others. So the basic discrete probability thinking is the basis of being able to deal with such data in the future. We met the binomial, the very basic one. So I think most of us maybe met that previous in our lives. Now another one, which is a bit close to the binomial, but then again, not quite the same. I have two formula slides, but I will start with the third example slide because I prefer to begin the story there and then go back to the formulas after that. Consider the example that we will be playing with a little bit. It's a classical quality control example. The hypergeometric comes up various places, but quality control is one of the places where it maybe hits us in the face when we are a production engineer or quality engineer or whatever, managing production person. Let's consider we have 10 items, in this case hard disks. Let's also, for now, that's a bit funny about those examples, that in a way we are assuming that we know the truth, and then you can say, then why bother if we know? But it's just to make the example, right? So let us assume that we would know that 2 of them actually are with faults. So it's a scenario of what might hit you, right? 10 are there, 2 of them are actually not good, 8 are good. And then imagine we were to do some quality control sampling from this little toy sample or toy shipment of 10 hard disks. Let's consider that we decided that we have the time in our business to actually check 3 of them. We don't have time to check all of them. We only have time to check 3 of them. So we take 3 at random out of those 10. And then we could ask various probabilities. What is the probability that, here it's asked, what's the probability that we find at least one of the 3 that has scratches? What's the probability of 0? What's the probability? It could be all of the questions. Could be there. Here's one specific of them that we are asked to find. Let's think about the process here. In a way, it looks a bit like the binomial, right? We actually take a random sample of 3. That's the sample. 3 times. There are 2 possible outcomes each time if we sort of consider them one at a time. It could be either it's okay or it's not okay, right? So that's the binomial outcome of each individual of the 3 that we take. But that's exactly the point. The way we take them, the way we sample them. What do? I would say we would probably do the following. We would take one of them at random. Depends on the size maybe, but that's the practice. We have the 10 there on the desk. We throw them. No, we don't throw them up. We take a dice, and then we take at random one of the 10. Then I go to the hard disk box. I open the package and I check. It looks okay. I put it back. I fix the box again. And then what do I do with the box that I just checked? I would say most people with an intelligence level at a very minimum number would take this box and set it aside, right? And then it would sample at random from the remaining 9. And then someone, whoa. Don't do that, the theoretical guy would say. Don't do that. Because now you ruin the binomial assumptions. Because now you changed the setting. Now there is not the same probability of finding it because you took one out of the game. No matter whether it's one or the other you took out of the game, you would have ruined the game. The binomial game was ruined because the p is no longer the same, right? So the theoretical guy would say, don't set it aside because then I don't know how to compute the probabilities. Make it back. Do it with replacement. Okay, the practical guy, I put it back in the pile and then I sample again. You won't do that because, hey, then you pick the same one again. I think I just had that one before. Well, I'll open it again and check it's once again. You don't do that, right? So the binomial doesn't work. You take one at a time without replacement, right? Which is the same as taking a handful at random, sort of simultaneously, right? Like that. 3 at, if they were small enough, you could do like that. If it was small balls in a bowl, you could take a handful of 3 like that. 3 without, that's also without replacement, right? So we need to think about how to deal with those probabilities sometimes. Here is the way to think about that. So we are going to have some numbers in play. We are going to have a name in the R. Now here's a bit of a, in the notes, there is one notation. In the R function, there's a slightly different notation. Sorry, but that's life sometimes. If you go to MATLAB, you'll probably have a third notation. If you go to Excel, you'll have a fourth notation. We'll have to live with different notations for the same things when we are engineers. Here is the book notation. The book notation would call the sample size, not the sample, sorry, the population size would be capital N. That's 10. That's the total number of hard disks, right? Then I have a name which goes like the name in the binomial. I have a name for the sample size. That's the handful of 3. And then I have a name that corresponds to the level of the probability p actually, but here it's given as numbers. I call the number of successes. I say it's a generic term, this successes, for what we count. Sometimes successes could be something not very good. It's just a term, like a binary thing, 0, 1. Successes is the name for what we count, be it good or bad. So we count, we have 2 A's, right? A, capital N, A, and N. When I have these 3 numbers, how should I get the probability? What's the probability of, for instance, well, if we want to solve the exercise, the question given in the exercise, it's not because it has any particular meaning, it's just as one of those probabilities. The question was, what's the probability that at least one of the 3 has scratches? That's 1, 2, or 3. Well, of course, 3 couldn't happen here, but still, then is the probability of 3 would be 0. But we could turn that around and make that into a probability of having 1 minus 0 with scratches, right? Because that's the complement to being 1, 2, or 3. It couldn't be 3, of course, here, but 1 or 2. Now, would we, by just some combinatorial thinking, I think most of us in a good period, at a good time, Friday afternoon between second and third beer, that's where we could solve this combinatorial exercise by ourselves. Just before, not. Later, not. Between, that's a personal thing, of course. That's for me. That's my peak. That's Friday afternoon between second and third beer. 15 minutes later, I'm dead. So that's where we peak. What's this probability? Well, maybe I should think a bit of combinatorial thinking here. What is the total possible number of samples of 3? I take samples of 3 out of 10, even though we didn't spend many minutes on discussing the combinatorial parts of this. This was the one we gave this name last lecture, the binomial coefficients. The number of different ways we can have 3 out of 10, the number of different positions you can have in an ordered sequence of 3 out of 10. That's the total number of possible outcomes. Now, the outcomes that matches exactly 0, that means that I should take 0 out of the 2 with scratches, and I should take the rest of the 3 that I take out of the remaining 8, right? Here is the hypergeometric probability density function, given by those specific choices of A, capital N, and small n. We should take 0 out of the 2 because that's the probability I'm aiming at, and then the rest of the 3, because I'm taking 3, should come out of the 8 relative to the total number of possible outcomes, 3 out of 10. That's hypergeometric probability distribution. In general, with not 2, 3, and 10, and the 8, that's 10 minus 2, right? So that's the general formula here, the same formula but with the general context. And to go back, I should change the order of these slides next year. To have them in the order I like them better. We have this notation. It's about sampling without replacement. Yeah, well, I've said it all by now. So that's the hypergeometric distribution. We can play around with that in R. Let's see, here's a summary. If we talk about those small sampling quality control situations, at least for now, it could have more consequences for things we're going to learn later in the course, but still. Binomial distribution is used to analyze samples with replacement. Hypergeometric is used to analyze samples without replacement. Actually, there is a gray zone area here. When our sort of different, what's it called, election, Nielsen, AEM, you name them, they do polls. That's the word I was looking for. Election polls. When we have all the elections, they would also sample people, right? Then they sample people in the population of Denmark, say 5-6 million, and they would ask them, do you vote for Lille Lars or do you vote for? It's gonna be Mette, beautiful Mette next time. Lille Lars and nice Mette. Pretty Mette would be the cause. Are you down with Mette? No, don't, or are you not? Do they sample with or without replacement, you think? Have you ever, you sit at the dinner, someone calls you and then asks, would you participate in a survey? They ask you friendly. I don't know how you answer. How do you answer usually? I go, fuck you, in a very friendly way. Because I also know that they are nice and friendly young boys and girls working at these companies, calling to old and grumpy men like myself. So we should remember to be friendly, of course. But then what would happen if they called you a second time and they said, whoa, you were the lucky one. You were put back. You were put back with replacement and then you were selected again. I'd like to hear your answer once again. That's not what's happening, no, right? They do replacement, they do sampling without replacement. However, I'll assure you, they do a lot of computations based on the binomial anyway. They don't care, sometimes. They don't care. The thing is, if the n is very large, right? If we have a large population, we'll get back to those then we could say hyper almost equal to be a bit loose in my formality here, right? Because if I just sample a few hundred out of some millions, right? The proportion p, I don't change the proportion really to any important. Maybe I change the p at the 15th decimal point or something like that. But that wouldn't really change the probabilities at the 4th or 5th decimal point at all. So when sampling relatively small samples from really large populations, where I maybe should use the hyper, then I could just as well use the binomial because it gives me the same answer. And for many reasons, that makes many things easier. It's just to say, so yes, there is a distinction, but yes, in many contexts, it doesn't really matter much if we are in big numbers. Anyway, that's the hyper. We need to maybe just check. Here is the same probability in R, and note, please remember, if you're in doubt about the options in a function, I mentioned that already, go question mark R hyper or D hyper. And even though I know it's small for you there, when you sit with your own computer, you can read what the M is the number of scratches, the N is the number of corrects, or as here called white and black balls. So the sum of little m and little n would be the capital N in our case. Anyway, you can find out about what these things means compared to your notation by looking at the help function, right? That's what I said. They use M, N, and K, and that is a different naming than what I just showed you. Here it is. That's the hyper. There you are. You're being tricked a little bit now because I'm a bit not in control of the structure. But anyway, you should know. This is a picture from a DTU testing place, actually. Of course, we could discuss the blue one. That was a trick thing. The trick thing, I agree, the blue one could be the truth. But I wouldn't know, because it doesn't have to be a 50-50 case. But I can understand why you would pick the blue one. Anyway, so it's not completely silly, but you're not going to win now. I have one more for you. Good job, Emilia.